We are now going to solve the exercises of this section. So in this first one, we have to prove the first inequality of lemma 752. So let's recall that part of this lemma. In this lemma, we are given a sequence of positive real numbers. That means each Cn is positive, is a real number and is positive. We then have to prove this. The limit inferior of Cn plus 1 divided by Cn is less than or equal to the limit inferior of the nth root of Cn. Okay, so let's see the solution, how one can prove this. So what we are going to do, just like the other inequality that we proved in the text itself, which involves suprema, here also we are going to name one of these, say L prime. In the text we considered the limit superior of these ratios to be L, and then we worked with that L. So here similarly we are going to name this one L prime, and then we will see where we can go, what we can do with that L prime. Let L prime be the limit inferior of these ratios as n approaches infinity. In the beginning itself we notice this, since this sequence, because that's the sequence we have here, this sequence is a sequence of positive real numbers. Our L prime is non-negative. How are we directly concluding this? Let us see. And this of course is a sequence of positive real numbers because each Cn is positive, so their ratios are also positive real numbers. Okay, fine. Now if one actually goes back to the definition of limit inferior and then tries to see what happens to the limit inferior of this sequence, given that it is having terms which are positive real numbers, then one gets this. So if you just simply take the sequence itself, the entire sequence, so what do you do first if you want to calculate the limit inferior of a sequence of real numbers? You first take the entire sequence and then you look at its infimum, that means the greatest lower bound of all the terms. Now because all the terms are positive, because it's a positive sequence, so 0 is already a lower bound for the entire sequence, so its greatest lower bound will be greater than or equal to 0. It may be 0 itself, but in general it will be greater than or equal to 0 and never less than 0. That means 0 is less than or equal to the infimum. To save space we can write like this. where n is greater than or equal to 1. Next, what you do, you calculate another such infimum, but now not of the entire sequence, but the sequence you obtain by removing the first term from the entire sequence. That means you next consider this infimum, where now this term is not there, it's not involved. So your n is greater than or equal to 2. But if you remove this term, the resulting sequence is just like this one, again a sequence of positive real numbers. So its infimum is also non-negative, like this one. And this way, all the infima that you would of course continue calculating these infima by removing more and more terms. So all these infima are non-negative. So their supremum, that is this thing, divided by Cn, as n is greater than or equal to k, where k itself is greater than or equal to 1. That will also be non-negative. In fact, that will by definition be an upper bound, specifically the least upper bound of all these infima. So automatically it is greater than or equal to all of them. So it's great that the object itself, that entity itself, is greater than or equal to 0. But this by your definition is nothing but the limit inferior of your original sequence. That means this is your L prime. So that's how L prime is greater than or equal to 0. So there is in fact no possibility for L prime to be minus infinity. In general, we know that when we calculate the limit inferior of a sequence, it may be plus infinity, it may be minus infinity. Those two possibilities are there. Here, however, minus infinity cannot appear as one possible value of L prime. So that's why, and not just minus infinity, it itself has to be non-negative. It cannot be a negative real number also. Now that means we have two possibilities left for us. Either L prime is equal to plus infinity, or it is not equal to plus infinity. That means it's a real number. So we are now going to look at both of those possibilities separately. So let us first see what happens when L prime is plus infinity. Let L prime be equal to plus infinity. Okay, then for every, okay, let me write from that side. Then for every positive integer m, there exists a positive integer n such that m is strictly less than Cn plus 1 divided by Cn for all n greater than or equal to n. Where is this coming from? This is coming from, oh, we need to mention that now, by proposition 6 4 12, I think. Yeah, 6 4 12 a. What does this proposition say? This part of the proposition, it says that if we have a sequence, say you have some sequence of real numbers, and say L minus, this is the standard notation for the limit inferior, L minus is the limit inferior of an, okay, and say you have some extended real number y less than L minus, then by part A of this proposition there exists some integer n greater than or equal to this smallest index m, such that an will be, an means the original terms of the sequence, they will be greater than y, strictly greater than y for all n greater than or equal to n. Now in our case, our sequence is of course this sequence, so our an is Cn plus 1 divided by Cn, and L minus is of course our L prime, because that's what L minus is for this sequence. Now because we have considered the case where this is plus infinity, so it does not matter what positive integer m we choose. Imagine m in place of y. Y is always strictly less than plus infinity. This is plus infinity now, and that is why by this part of the proposition you will find an integer n greater than or equal to m, but because our smallest index is 1, I mean the smallest value of the index n is 1, so here n is greater than or equal to 1, and that's why we are saying there exists a positive integer n such that an is greater than this y, that is m, for all n greater than or equal to n. That's how we are getting this thing. Now this is a place where the situation is somewhat like what we have already seen in the text, the part in the text where we have the proof, namely the inequality involving supremal. So we can proceed accordingly. This implies Cn times m is less than Cn plus 1 for all n greater than or equal to n. Keep in mind that we are able to write this inequality from this because we can multiply on both sides by Cn, and doing that the inequality keeps its direction, it does not get reversed because Cn is positive. Okay, that is So if you write the first few instances of n, what will you get? You are actually not looking at a single inequality here, but infinitely many inequalities depending on the value of n. So the first one is you obtain it for n equal to capital N. So you get these things. Cn times m is strictly less than Cn plus 1, then Cn plus 1 times m is less than Cn plus 2. Let me write another one. 2 times m is less than Cn plus 3, and so on. It goes like this. Now using these inequalities, we can get one thing, that a similar thing we got in the text also. Using these, shall I write like this, or let me just, because I have written the inequalities in detail like this, so let us just see what we get from them instead of simply writing the final result. Hence, okay, now if we multiply on both sides of this inequality by m, then what do we get? Cn times m square, which is less than, let me maintain the order, write Cn plus 1 first and then m. But this is less than Cn plus 2. Here also, have you noticed that thing, that the inequality does not change direction because we are multiplying on both sides by m, and m is a positive integer. And you can now understand that we can keep doing this. Just to show another one, that's why I have written one more. So I will write another one, the next inequality that comes naturally if we follow this pattern. Comma, then, okay, now your inequality is this: Cn times m squared is less than Cn plus 2. Here also you multiply on both sides by m. Doing that, you will get Cn times m cube is less than Cn plus 2 times m, which is less than Cn plus 3. In general, we have, and which of course can be proved by induction, Cn times m to the power k is less than Cn plus k for all integers because things are actually starting from Cn. So let me just make k non-negative. I allow for the possibility k equal to 0. If you put k equal to 0, you get the original inequality. Now writing, note one more thing, that these inequalities, this next set of inequalities is also infinite. This is the original inequalities, of course, the first step. I mean, it is already there, but from that, then you get this next one, and then you get this next one, and you keep on getting like this, and it doesn't end. And to show the fact that here also we are looking at infinitely many inequalities, we have this variable k, but n is fixed. So we will now just change the names a little bit and express the same thing in a slightly different manner. Now writing n equal to n plus k, we get Cn times, so in place of k you would put n minus n, and in place of n plus k, of course, you would put n. But how will you show the variation now? As k is greater than or equal to 0, as k varies over all the non-negative integers, n varies over all the integers greater than or equal to capital N. Okay, and now we are going to use these inequalities in this next set of calculations. There are many results are going to be used. Let me just write the things and then we will see each one of them one by one. Thus, by the limit laws, that is one thing. Then exercise 642, lemma 6.4.13, proposition 6.4.12, part F, and lemma 6.5.3. Do not be bothered by this long list of results that we are writing here. That's because usually we do not do such things. Here, however, since the things are somewhat confusing and critical, so I have decided to show everything. And I am also going to say in which step which ones are being used. That also I am going to show. And lemma 6.5.3, we have, let me write in this fashion, it will look good. M is equal to m times limit of Cn times m to the power minus n, its nth root. That too, I am putting a star over this limit. We will justify what this star is and why it is there. In the next step, we take the m inside. And then, in place of ordinary limit, we are writing limit inferior, that too with a star. Okay. I forgot to write one more thing, and that thing is, shall I be able to show it here? I mean, I have already written this part, but before that I needed to write something else which comes from this inequality. Can I not show that thing here itself? Okay, let me just show it here itself. So what is happening here? You see, m is already there, and here we have an nth root. Now if I bring this m inside this nth root, then it will not stay m, but it will be the nth power of m. And you can do this because m is a positive integer, it's a positive real number. That's why its nth root of its nth power will give us m itself. So there is no problem with that. And you can see that this is nothing but the nth root of this side, and this is less than or equal to the limit inferior of Cn 1 over, and there is one more step, and after that we will have to justify everything. And this thing is itself less than or equal to the ordinary limit inferior. And within brackets we write star denotes the fact that the sequences involved start from n instead of from 1. So what is this now? Note one thing, that okay, first of all, we are using which one? This one. What does this lemma say? This lemma says that this limit exists and its value is 1, where x is a positive real number, and in place of x now we are having this thing Cn times m to the power minus n. Is this x a positive real number? Cn of course is positive because it's coming from our positive sequence. M is a positive integer, so its integral power, no matter what the exponent is, here the exponent is minus n, it is also a positive real number, so their product is a positive real number. Okay, so that means its limit is actually equal to 1, giving us m itself. So in place of m we can write m times this. But what is this star? Star denotes the fact that the sequences involved start from n, because our sequences actually are starting from 1, but the inequality that we have here, or rather I should say inequalities that we have here, they are from this stage. So whatever sequences we will be using here, since we are varying in, that means we are considering some sequences in each such step. Those sequences are starting from capital N. So to distinguish that from the corresponding limits that you are seeing here of that version of these sequences which start from 1, to make that distinction, I have put a star here. We do not have any special notation for this. I mean, if you just simply look at the limit of a sequence, you never know what the starting index is, and actually does not matter, because in most of the cases, whatever the starting index is, the limit is unchanged. I mean, the limit, it stays the same. But here, because we are dealing with limit inferior, ultimately there the starting index somewhat matters. So that's why we have to keep track of this thing that we are, or we have to keep ourselves reminded all the time that we are dealing with sequences where the index is starting from N. So that's why a star. So it just simply means that if I cannot get rid of this part. Okay, you understand the first step. It's just ordinary limit of this thing is equal to 1, and the index is starting from capital N, that's why this star. Okay. Now because this is ordinary limit, you can use the limitless, and you can take this constant m inside the limiting process, because this m does not depend on n. This m is our chosen positive integer m. So there we are using the limitless in this step. Now limit has become limit inferior. Why? That's because we know from proposition 6 for 12 part F that if we are dealing with a convergent sequence of real numbers, then its limit superior and limit inferior are all equal. So that's why this is equal to this, and that's where we have used proposition 6 for 12 F. Fine. And this part, of course, in this step I haven't done anything much. We have just simply changed the appearance of this, and we have used the usual rules of exponent m to the power n minus n. Okay. Now you come to these inequalities. You see that this thing is strictly less than Cn, where n is greater than or equal to n, and in fact it is due to these inequalities that we need this star, and we are having to use the versions of these sequences where the index starts from capital N. Okay. Now this thing is less than Cn, so by your rules of exponents, and note that here this part is positive, I have already said that, and this part is of course also positive. So this inequality would imply that the nth root of this is also strictly less than the nth root of Cn. So that's why I was saying that I have to write something else. Actually I should have written after this line that the nth root of this is less than the nth root of Cn for all n greater than or equal to n, and then I should have continued like this. But anyway, so this nth root is less than this nth root, and here you can use your comparison principle, which says that if we have such inequalities, then the limit inferior of this side sequence is less than or equal to the limit inferior of this side sequence. Keep in mind that in the comparison principles we have these inequalities, not strict inequalities. So although we have strict inequality here, that in general would give us this type of inequality. and that's not a problem for us. So in this step we are using lemma 6 for 13, which is your comparison principle. Okay, but now what about the final step? In the final step we have suddenly gotten rid of star. That means here in this step the sequence we are looking at is this sequence, where the index is starting from capital N, whereas in this step we are looking at the full sequence where the index starts from 1. And if you consider these two sequences, in other words, if you possibly remove some few terms from the beginning of this sequence to get this sequence, then its limit inferior likely decreases, or it just stays the same or it decreases. That means this limit inferior is less than or equal to this limit inferior, and this is why we needed to keep track of all these things, where the starting index, usually this is not needed, but in this case it's needed, and that thing we have already proved in exercise 6.4.2. Okay, so now the calculation is justified. So ultimately what we have obtained is that the limit inferior of these nth roots is greater than or equal to m, capital M. And this has implication. Oh, I need that start part, no? I wrapped that off also. That means I have to write it again. Here star denotes the fact that the sequences involved start from N. So M is less than or equal to this thing. But M was our free choice. M is any positive integer. It does not matter what we choose M to be, it's always less than or equal to this. But M is a positive integer, so you can keep choosing it larger and larger and larger. So if your this limit inferior is itself a real number, at some stage M will just surpass this, and this inequality will fail, because if you choose this to be a real number, then you can always find a positive integer still larger than that real number. So that's why, since M is arbitrary, the only thing we can conclude is that this must be plus infinity. So this is our final conclusion that we are getting from the assumption that our L prime is plus infinity, and L prime was the limit inferior of Cn plus 1 by Cn. So in this case, that inequality that we are trying to prove, that has reduced into an equality, and both of them are plus infinity. So in this case, so that means we are done in this case. Equality means automatically less than or equal to also by definition. So that means now we can assume L prime to be a real number. And we have already seen in the beginning of the solution that this L prime is non-negative, it's greater than or equal to 0. If L prime, should we mention that once more? Because in the solution that thing is left behind. So let us once again recall that fact. We have L prime greater than or equal to 0. Now if L prime is equal to 0, then L prime is automatically less than or equal to this. Why? Because just like L prime is the limit inferior of a sequence of positive real numbers, namely Cn plus 1 by Cn, because of which it has become non-negative, just like that this is also the limit inferior of a sequence of positive real numbers. So it is also by following the same arguments non-negative. So in this case also we are again getting the inequality that we are trying to prove. Note that this is also a sequence of positive real numbers. So now we can further narrow our search, or I should not say search, but narrow our attention to the case where L prime is strictly greater than 0. So now assume this. Okay, now we are going to work with this type of L prime. Again we have to show that this, even in this case, this L prime should be less than or equal to this limit inferior. Choose any epsilon, a real number, such that epsilon lies between L prime and 0. Because you see, we are whenever we normally choose epsilon in analysis, we choose it to be positive, but that epsilon, if you choose it arbitrarily, it can either be greater than or equal to L prime or less than L prime. So we are concentrating on this case first. Then again by proposition 6 4 12 part A, there exists a positive integer in let us take n prime this time, such that L prime minus epsilon is less than this for all n greater than or equal to n prime. And this time you understand what we have done, because we have done a similar thing before. And now the y that we have here, I mean I'm talking about the application of this proposition here. In this case, the y that we have is L prime minus epsilon. And note one thing, that L prime minus epsilon, this expression makes sense and is itself a real number, because now L prime is a real number, and that too it's a positive real number. Positivity, however, has nothing to do with this. It will come later. So what I am trying to say here is that if you just simply generally use an expression like this, then if your L prime is minus infinity or plus infinity, then this becomes meaningless, because such algebraic expressions have not been defined in the system of extended real numbers, but now we can. So this y is less than all the terms of our sequence Cn plus 1 by Cn starting from some stage, and that stage is n prime. That is Cn times L prime minus epsilon is less than, you can understand that we will then go through similar steps here like before, for all n greater than or equal to n prime. Now instead of repeating things, we are just directly going to write like this: from this we get Cn times, not Cn but Cn prime, because now the thing is n prime here. Cn prime times L prime minus epsilon to the power n minus n prime is strictly less than Cn for all n greater than or equal to n prime. Now writing a prime equal to the constant part of this expression, that means Cn prime times L prime minus epsilon to the power minus n prime. Writing a prime equal to this, now we can change the appearance of this. If you are wondering why I took A prime and not just simply capital A, that's because capital A has already appeared in the proof that's there in the text. So I have just decided to use another symbol. But to show that it plays a similar role as that A, I have kept A, but I have decided to call it A prime. Writing this, we get, so what shall we get now? A times C will not appear. L prime minus epsilon all to the power n is less than Cn for all a prime, not a, for all n greater than or equal to n prime. And this time we are not going to keep things unfinished. We will write this implies a prime to the power 1 over n times L prime minus epsilon. It will just simply be that, and Cn to the power 1 over n for all n greater than or equal to n prime. Okay. Now, did you notice one thing? I have not just simply written this step for completing this calculation, but there is a point here that needs to be noted. What are we doing here? We are taking nth roots on both sides, but can we do that? In order to be able to do that, the bases that we have on both sides should be positive. For negative bases also you can take roots, however you have to be extremely careful. Here, however, we do not have those problematic cases. All the things are positive. How? You see, it all starts from this type of choice for epsilon. Because of this inequality, L prime minus epsilon is actually a positive real number, and that is why this part is positive, and the way we have defined a prime, this is also again positive, because this is positive and this is already positive. It's coming from our positive sequence, so that's why taking nth root on both sides is legitimate. Okay. Now, by the limit laws and lemma, what is the number 653, the limit of this sequence first of all it exists because of these two things, and again by this laws it is equal to, see, I put epsilon prime, L prime minus epsilon. This type of mistakes are common and should always be avoided. So this is where we have used the limit, one of the limit laws, and by this lemma this is equal to 1. So that means this is L prime minus epsilon. Hence, by the comparison principles again, so now if you proceed just like those calculations, you will ultimately get this. You will ultimately get what? L prime minus epsilon will be less than or equal to the limit inferior of Cn to the power 1 over n. This is obtained by following similar arguments as above. You know what we are talking about here, that calculation. which needed many results for its justification. Like that, if you proceed in this case, you will ultimately get this. This is obtained by following similar arguments as above, or you can make it even more clear by writing these things, that is the case where L prime is greater than 0 or the case where L prime is a real number in a separate paragraph. Then you can write this is obtained by following similar arguments as the previous paragraph or the paragraph above. Okay, now just from this inequality we cannot immediately conclude anything, because keep in mind that our epsilon is not any epsilon greater than 0, but rather a special type of epsilon, namely which is also strictly less than L prime. If we choose, on the other hand, if we choose epsilon to be greater than or equal to L prime, then L prime minus epsilon is non-positive, that means it's less than or equal to 0. However, this limit inferior is already non-negative, that we know. Thus, for any epsilon greater than 0, we have L prime minus epsilon less than or equal to the limit inferior of this sequence, whose nth term is this. And this implies that L prime itself is less than or equal to this. So that means in this case also we have our inequality that we were trying to prove. If you see, there will be one more, maybe there you will, if you look carefully, you will see that even then one can run into a type of problem, because I hope you understand how we are getting this from this. It's the fact that these inequalities are true for all epsilon. So if you do not assume this and have the opposite inequality, that is, you will then have L prime strictly greater than this, then you will get a contradiction. However, what happens if this limit inferior is itself plus infinity? What happens in that case? Oh, in that case actually you do not have to do anything. If this is plus infinity, then your inequality is automatically true. Okay, so there is no problem. So we are done. So this completes the solution, and it also completes the proof of this lemma 752. There are two things that I argue to go through in detail here in this solution. One is how we obtain this thing, that means that big calculation. What that calculation is specifically in this case, that is one thing. And another thing is How would you use this to show that L prime has to be less than or equal to this? This is in fact something, this second thing that we have already done when we developed the system of rational numbers. There you go back, one of the exercises is just this. From that you will get your idea. But anyway, the solution is now over. Okay, so having gone through this much theory, let us now see an application. Let x be a real number with its absolute value less than 1 and q be a rational number. Show that the series summation n to the power q times x to the power n, where n varies over the set of positive integers, is absolutely convergent and that the limit of the sequence whose nth term is this is equal to 0. To show this, once you have this, you don't in fact have to do anything, because it follows directly from the zero test. You know that when a series is convergent, not just absolutely convergent, simply just convergent, then the limit of its terms is 0. It exists and is 0. So accordingly we start the solution by the zero test. It's enough to show that the series is convergent, because then this is just a simple consequence. Now, due to the somewhat general nature of this series, you cannot just directly apply, say, ratio test or group test. You have to do something. It's because of the presence of this q, which you can treat as a parameter. So if you change q, the series actually changes. N of course changes within the series itself, but here you are not looking at a single series but infinitely many series. So by the zero test, it's enough to prove that this is absolutely convergent. Let me just refill. I think I am running out of ink. Okay, so now we have to do something about q, and that thing is this. Choose a positive integer n greater than the absolute value of q. Why suddenly such a choice is made, that you will realize once the solution is over. So in this kind of solutions, usually what happens is that we would of course we would try to immediately apply a test, say the ratio test or the root test, and then we will see what are the things that we need, and then we will try to prove those things, and from that these things come. So when you look at it directly, it looks a little strange. Then minus n is less than q, which is less than n. You know that these inequalities are equivalent to that one. So by a result, which result? This is why names are better than numbers. If you want to recall something, names are better. By proposition 673, you have this. For all positive integers n, that means if you have some real numbers, we are the exponents that we see in these inequalities, that is minus n, q, n, these are all rational numbers. So in proposition 673, you have these inequalities, so that will imply that you have these inequalities. The only condition, I think, if I am remembering correctly, is that the base of these powers, which in this case is 1 plus 1 over n, should be greater than 1. If it is less than 1, the inequalities will get reversed. Here we can clearly see that this is greater than 1, because 1 plus 1 over n for all positive integers n. Now by the limit laws, and if we want, we can mention it, and proposition 6.1.11. It's not a very big deal if you do not mention it also. I will say why. proposition 6111 just says that the limit of 1 over n is 0. That's just the thing it says. So that's why if you do not want to mention it, then it's okay, because it's something very fundamental and simple. So that's why the limit of 1 plus 1 over n is 1, that is coming from the limit clause. So the limit of its nth power is also 1, that is again coming from your limit clause, and hence the limit of the reciprocal of this, which is just this, is also 1. But this sequence is trapped in between these two, and they have the same limit, so you can apply the squeeze test. So by the squeeze test, the middle one will also be convergent and its limit will be the same as this common limit. Hence, if we now okay, so if we are taking so we will just directly have something like this, again by one of the limit clause. This times absolute value of x, this thing is just simply absolute value of x, and this is less than 1, which is given. Now we will apply the ratio test to the series, but that also cannot be just simply applied. There is a condition that should be met. Note that the series is absolutely convergent if x equal to 0 in an extremely trivial way. This is just something we did not even bother to verify. It's convergent. So we assume x to be non-zero. Now we have got a series given that x is non-zero, whose terms are all non-zero real numbers. X may be negative, that is allowed, but x is not equal to 0. So now we are in a position to apply the ratio test. We note that the limit of the n plus 1th term, that means this divided by the nth term, and that too not just simply that, the absolute value is equal to if after rearranging things and doing all the necessary things, you get this. Yes. and this is just equal to this, which is less than 1. So by the ratio test, the series is absolutely convergent. Keep in mind that this condition should be there, otherwise we will just get stuck here and then we won't know anything. Note one more thing, that we not only have n here, which will make the terms really large, but we also have q here. Q, however, is not varying, q is fixed. You can take q, still you can take q to be extremely large. For example, you can consider this series. Now this exponent is an extremely large number, really excessively large, but provided your x has absolute value less than 1, still this is convergent. Okay, so that is a somewhat counterintuitive aspect of this series. But anyway, so this is the completion of the solution, and because of this convergence, automatically that limit also is equal to 0. Limit of the terms of the series is also equal to 0 by the zero test. And then there is one final one. Let's just complete it. Irrespective of how large the video has already become, give an example of a divergent series divergent series of positive real numbers. Yes. AN such that this limit is equal to okay, let me just write 1 because I don't have space, equal to 1, which is equal to limit an to the power 1 over n, and give an example of a convergent series. positive real numbers Bn such that, again just like those limits, here also this limit and this limit are both equal to 1, so that you will not be able to infer anything from either the root test or the ratio test. So this exercise in fact completes the root test and the ratio test by showing that when the conditions that we have in those tests, which one of them shows convergence, one of them shows divergence, if they are not obtained, then in the other cases we cannot infer anything. Both the sides are present. Convergent series are also there, for which this becomes 1. Divergent series are also there, for which this becomes 1. So from 1 you cannot say anything whether it's convergent or divergent. This is equal to 1. And there is a hint. Use corollary 737 and a remark. This shows that the ratio and root tests can be inconclusive. Can be inconclusive even when the summands are positive. And the limits converge. Even in that case, things can go wrong. I mean, we will get stuck. And the solution is not very big. Solution is small. We just have to give 2 examples, and that's all. In giving one of the examples, namely the example of a convergent series, we will use that corollary. So first we need to come up with a divergent series of real numbers where all the terms are positive, such that these limits are equal to 1. And there is a very easy series. Consider the divergent series summation an where an is equal to 1 for all n greater than or equal to 1. That means it's the series 1 plus 1 plus 1 and so on. It's definitely a series of positive real numbers, and we know that it is divergent because its sequence of partial sums is just the sequence of positive integers which has no limit. So that's why it is divergent. And if you calculate these limits, of course you are going to get 1, because all the terms in this sequence are 1. This is the constant sequence 1, so its limit is 1, and these nth roots are just 1th roots of 1. First root of 1. So here also you are dealing with the constant sequence 1. So these limits are also equal to 1. I am not going to write these things, okay. And for the second one, you consider this series. Summation Bn, where Bn is equal to n to the power minus 2. So that means here you are dealing with this series. By corollary 737, which actually says something about the convergence of this type of series, where instead of 2 in general you have p. Now it says that when p is greater than 1, then that type of series is convergent. Here p is 2, so this is convergent. In fact, it's absolutely convergent. So this is absolutely convergent, and also it's a series of positive real numbers, because 1 over n square is positive no matter what n is, right? But what about the limits though? Let us see. What about this? After manipulating the expression, you will see that the limit turns out to be equal to 1. Hence, because this sequence is convergent, its limit inferior and its limit superior will also be equal to 1 itself. So that means this is 1 and that other thing is also 1. However, by the lemma 752, we have this also, no? And this is also equal to 1. So being trapped in between these two ones, this is also 1, this is also 1. So again, by proposition 6 for 12f, because limit inferior and limit superior are both equal to 1, so the original sequence is convergent and its limit is equal to 1. In order to get this limit, you need not, however, follow this argument only. You can also use that one thing. Huh? You have already proved that this limit is 1. In fact, it was one of the corollaries to this general result. That also you can use. So that's it, that is just your solution. So these are the two examples showing that both the root test and the ratio test can be inconclusive even when your series is having only positive real number terms and not just limit inferior or limit superior. The limit itself exists, but all the limits are 1. And this ends this section entirely. and it ends the chapter also on infinite series. After this, I think we have functions, real valued functions, their limits, their continuity, and now slowly we are entering our usual calculus. So we will see where things go. And tomorrow of course we don't have any upload. Day after tomorrow, because we have already gone through graph theory, right? So day after tomorrow, ideally I should I should again do group theory from Herstein, but because at least one of you is very eagerly waiting for calculus, so we will do calculus day after tomorrow, that means on Tuesday. So with that, I wrap things up for tonight. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address. So see you day after tomorrow with calculus. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.